Assalamualaikum everyone. I hope all of you are doing extremely well. So I'm back with another video. I was actually kind of busy with some exams. So in today's lesson, we would be covering the question 21 to question number 30 of your May June 2020 paper 1-2 for A levels. I'm sorry for the delay that happened for this video, but let's get into it. Okay, so question number 21. The table shows the molecular formula of three molecules, PQR. None of the molecules are cyclic, so that's something important, right? None of them are cyclic. Which molecules show a strong absorption between 1610 per centimeter and 1750 per centimeter in the infrared spectra. So before I actually dive into the the data booklet, which will have something like this, let's first try to deduce what each molecule basically is. Now, for the case of P, if you closely observe, you have carbon which has all four hydrogens as well as an oxygen. And if you have a carbon which has the maximum number of hydrogens, for example, in the case of alkanes, it's CH4. And along that, if you also have an oxygen, it would always be an alcohol. So this has to be for sure your, wait a second, please. So this for sure is your CH. My pen is actually low on battery, maybe. That's why it might not work properly today. My apologies for that. So you can clearly see this is basically your methanol, okay? And what about Q? So in the case of Q, I see two hydrogens and I see two oxygens, and that's something I would actually observe for a carboxylic acid. So HCOOH, and you can basically count. So one carbon, two oxygen, and then two hydrogens. And your R is CH2O, which is more or less it's that's something you get to see for aldehydes mainly. And what I'm assuming is it's going to be CHO. Now, many people might ask me at this point that, how are you being able to deduce these formulas or the structures? And my answer to them is basically the fact that, as long as you're practicing, you will get to that point. It's all about intuition when it comes to organic chemistry. The more you practice, the more it actually sits in your brain and becomes easier to, comprehend things. Okay, so the structure, I hope, for this is clear. It would be like C and then a double bond and then OH. And for the case of your methanol, I hope you would know that it will look something like this. Okay, now we need to see a strong absorption between 610 and 1750. So let's dive into the table. And so I'm looking for a value 1610 to, okay, there you go. So although it doesn't start with 1610, it does go from 1640 to 1750, and we want a strong absorption between 1610 and 1750. So there is a huge range that has been given to us. And so what we see here is a C double bond, and they have given you some some of the molecules that might have this C double bond. And so you can most definitely see that this C double bond is or will be responsible for absorption from approximately the 1640 or 1610 to 1750. And if you observe in these molecules that we have drawn, that's definitely the case for C double O in this case, which is Q, right? And there's also C double O in this case, which is for the case of R. So our answer should be C, which is Q and R. Moving on. Question number 2. Which row correctly shows the type of mechanism each of the two reactions Okay, so for this question, it's all about, in this case, for memorization. And just to make it easier, I've made this diagram for everyone. So just understand this. There are other reactions. There's reduction, oxidation, and other reactions. But when we talk about some of the fundamental reactions which involve either an electrophile or a nucleophile, and which are either addition or substitution, this is something to remember. Your alkenes only and only undergo electrophilic substitution. They don't undergo any of these three. Okay, they only undergo electrophilic substitution. And I might explain why that is the case for each of these in a separate video, but to keep it short, alkenes will always undergo electrophilic substitution. As far as your haloalkanes are concerned, they will always undergo nucleophilic substitution. And about alcohols, I will not say this very firmly that for alcohols it will always be nucleophilic substitution, but for many reactions, yes, alcohol does show a mechanism of nucleophilic substitution. For nucleophilic addition, it's always going to be carbonyls, which can be a ketone or it could be an aldehyde. And my most favorite, which is electrophilic addition, and that's something that you need to remember, that this is a part of A2. Okay, this is the part of the second year, and this electrophilic addition is only undergone by benzene. So as long as you remember this, there's a bit of ambiguity for alcohols because you do get to see a little bit of variance, but for all of those, just remember this strictly. So coming back here, what do I see here? I see a basically haloalkane, and haloalkane undergo what? Nucleophilic substitution. So not electrophilic substitution, it would be nucleophilic substitution. What do we have here? We have a ketone, which is propanone, and if you see, your carbon as a ketones undergo nucleophilic addition. So it's going to be basically, your answer would be D. Okay, moving on. Question number 23. Ester X is shown. Ester X is hydrolyzed, okay, and it is hydrolyzed using aqueous sodium hydroxide, and they're saying what is the molecular formula of one of the products. So firstly, visualize what this ester is going to look like, and this is what I've drawn for you. And I'm hoping that by this time you would know that this part is the acid part, right? With the part which has a C double O bond will always be the acid part, and the part with the O will always be the alcohol part. And when you basically hydrolyze an ester, you get to see a breakage of bond right here, which is between C and O. Not the C double O, but CO. And what goes to the alcohol is basically, what goes towards the alcohol is a hydrogen, and what goes to the acid is the hydroxide. So what happens in this is basically an example of hydrolysis, and in hydrolysis what that means is that you break down a molecule with the usage of water. So what happens with water is that it breaks down into a H positive and a hydroxide ion, and this H positive goes to the alcohol and this hydroxide moves towards the acid, and then you get to see well, you will get to see this. But before I explain this, I hope this is clear, right? You get the alcohol, and an alcohol cannot react with an alcohol, right? NaOH. But here's the important thing. It's hydrolysis, well and good, we broke the bond and everything, but the important thing to remember is that we're doing this using aqueous sodium hydroxide, which is basic in nature. And when we break our ester, we end up with an acid and an alcohol. So this acid will actually react with that basic NaOH, and what you get to see, instead of your ethanoic acid, this actually ethanoic acid is formed, but it reacts with your basic NaOH and it forms what we call as the ethanoate ion. Okay, so these are our two for the molecular formulas for the products. So let's keep those in mind and head back. So C2H4O2, that's ethanoic acid. That would have been the case if there was no sodium hydroxide, maybe if we were using an acid for hydrolysis. This is ethanoate, which is sodium ethanoate. This is correct. C8H16O. Well, in this case, I'll come back to C because that seems a bit tricky. It might trick someone. But this is definitely not the case. This can only happen if you flipped between your alcohol and your acid when breaking down the ester. If you forgot and you thought this was the alcohol and this was the acid. Okay, about C8H16O, the problem with this is that if you come back, all right, if you come here, let's do the sum. This is 7 and then 8, C8, and then you have 14 hydrogen from here, 3 from here, 1 from here, and that makes it H18 and then O. So it's C8H18O, not C8H16O. So this can't be the answer. And why I knew this before I even went to count the molecular formula, the reason is because in alcohols, as I said for the first question, alcohols always have the max number of hydrogens. Just like in alkanes, it will always have a max number of hydrogens. So this will actually be CnH2n plus 2, right? Plus 2 O. So that's for a alcohol with a single hydroxyl group. This is going to be the general formula. So this is because this is the reason why I knew that this would be the answer before I even counted the molecular formula from here. Okay, moving on. Question number 24. Which reagent could be used to distinguish between propane 1,2-diol and ethane 1,2-diol? So I've drawn the structures for propane and ethane 1,2-diol above. Now, both of them are alcohols, and let's talk about alkaline aqueous iodine. That's the iodoform test, and in the iodoform test what we're looking for is a methyl ketone, basically, all right, or anything that can be converted into a methyl ketone. Now the thing is, if I basically come to my propane 1,2-diol, I do see the methane part, and what I do see is a secondary alcohol, and that's quite interesting. And I hope you have enough practice to realize that your secondary alcohol of this sort, right, which has a methane group attached to it, and it has a secondary alcohol part attached with that methyl, basically, not methane, methyl. That can, because what happens is that oxidation also occurs when we perform the iodoform test. So this CHO, secondary alcohol, gets converted into a methyl ketone, all right, and this is the reason why this will give a positive a positive iodoform test. In the case of ethane 1,2-diol, I don't see a methyl, so that's out of question, and there you go, the answer is A. For B, it's about oxidation, all right, because we're using aqueous acidified dichromate. It's about oxidation, and if you oxidize, I'll draw the structures here. If you oxidize your propane 1,2-diol, this part right here gets converted, because it's a primary alcohol, it gets converted into a carboxylic acid, all right, and this CHOH will get converted into a ketone, all right, and this part CH3 will remain as it is. So this is what you would get, all right. And for the case of ethane 1,2-diol, what you get to see is that this is a primary alcohol, this is a primary alcohol, and so this will give you what we call as oxalic acid, and oxalic acid looks something like this. Okay, you can call it a dicarboxylic acid if you will, but the better name is oxalic acid, all right. So there you go, and you can clearly see, even if we form these products, these are different products, but what do we achieve at the end? How can we actually distinguish a solution of oxalic acid and this acid right here? So we can't. So that's why B is not the answer. It says ethanol. Well, ethanol can't react with an alcohol, but it said a few drops of concentrated sulfuric acid. One important thing to note here is that in the entire A-level syllabus, whenever you read concentrated sulfuric acid, remember that it could only lead to two types of reactions. It could either be esterification, and that cannot happen because esterification happens between an acid and a base, an acid and an alcohol. In this case, we have an alcohol and we have alcohols, not acids. And the other reaction is dehydration, and that can happen for your alcohols. All right, and if you dehydrate these, well, what you will get alkenes. But then again, even if they're different alkanes, how would we be able to distinguish a solution of those? So it can't be C. And for sodium metal, well, it reacts with both of them, again producing some slightly different products, but then again, it doesn't really matter. We want a observable feature in the products that could help us distinguish between propane 1,2-diol and ethane 1,2-diol, and the answer is therefore A. Okay, it says which substance forms propanoic acid as one of the products when it reacts with hot concentrated acidified potassium manganate, and that's basically what they're talking about, is oxidation. And you can clearly see that all of these are your alkenes, and so I've drawn these alkenes here. I've drawn the structures. I've also drawn the skeletal formulas. I personally prefer skeletal formulas because they take much less time. But let's see. Now, what happens is that when you have hot and concentrated, when you have conditions which are hot and concentrated acidified potassium manganate, this is a strong enough oxidizing agent to actually break the double bonds. So this will actually break up your double bonds. It will break the sigma as well as the pi bond, whereas if the condition was dilute and cold, then the oxidizing agent would become mild, and in that case it would only be able to break the pi bond. But this is hot and concentrated, so it will break the pi bond completely. Now in the case of but1ene, what you can see is that when this bond breaks, whenever you have, remember, whenever you have oxidation of alkenes, first locate the double bond, break that according to the condition, and then if the condition states to break the sigma and the pi bond, whenever you see a carbon which is involved in double bonding, which has CH2, which has two hydrogens, remember it will always give you carbon dioxide and water. And the carbon which is involved in the double bond, which has a single hydrogen, will always give you a carboxylic acid. And this carboxylic acid, how did I get? I said CH3, CH2, and then CH, and over here you attach the OH. And what you get here is propanoic acid. And they asked us which of them will give us propanoic acid, and that's but1ene. But just for clarification, I'll also do B, C, and D. So this is the case for but2ene. In this case, when this bond breaks, this carbon has a single hydrogen, this carbon has a single hydrogen, both of them will become carboxylic acid. All you need to do is attach a OH here and a OH here. Both of them give what we call as ethanoic acid. For 2-methylpropene, this is again CH2, this gives you CO2 plus H2O. Now in this case, you have no hydrogen on the carbon which is involved in double bond, and in that case you get a ketone. So over here, when this bond breaks with this carbon, you get a bond, it bonds, basically makes a double bond with oxygen, and you get what we call as propanone. And for 2-methylbut1ene, what you get to see is, again, this gives you CO2 plus H2O. And if you observe, this is your ethyl and this is your methyl, and again you have no hydrogen on the carbon which is involved in double bond, and therefore it gives you again a it will again give you a ketone. In this case it's a butanone. Okay, so the answer for our question would therefore be but1ene. So all you had to do was you should have known the oxidation of alkenes, how it works, and then form the products and just observe them. Okay, question number 26. The structure of well, I don't know how to pronounce that, so I'll leave that, is shown. And they're saying that how many stereoisomers exist with this structural formula. All right, stereoisomers can be of two types. We can have geometric stereoisomerism or optical stereoisomerism. So what we're looking for actually are pi bonds. We're looking for pi bonds, and in optical we're looking for a carbon which is attached with 4 different functional groups. Not functional groups, but 4 different groups. First, let's go for geometric. I do see a couple of double bonds over here. Okay, so in this case we see a double bond here, and this will definitely show us what we call as geometric stereoisomerism. I'll just draw this bit, right? So one would be like this and the other one would be like that. All right, other one would be like that. So these will be the two types of stereoisomerisms, geometric isomers that you would get to observe. Now that's actually not stereoisomerism, because this is not between 2 carbon atoms, it's just C and double O, and with this oxygen you have nothing attached. And then coming here, okay, this is something important. These 2 double bonds cannot show you geometric stereoisomerism. The reason is, and here's the important bit, and write this down, that is your pi bond, right? Pi bonds within cyclic structures do not exhibit geometric stereoisomerism, and that's something important to remember. The reason is that these double bonds, there's no possible way, it's a ring, there's no possible way in which it can make this part and this part rotate in this way, or it cannot rotate it in this way. That's exactly the point. It cannot rotate it, and therefore there's no rotation possible. It's restricted, and in a ring there's no possible way in which we can make a cis trans. So remember this important point, and therefore arising from this single double bond, we will get two, one cis and one trans. Coming to optical isomerism, this has gone a bit dirty, so I'll remove these. All right, for optical isomerism, let's look at this carbon. This carbon is attached to 4 hydrogens and with this rest of the group, so this can't be optical because it is not attached with 4 different groups. Coming to this one, this is involved in double bonds, and carbons involved in double bonds can never be chiral, and the reason is because they would not have 4 groups around them. So not this one. This is also involved in double bond. This is also involved in double bond, also involved in double bond, also involved in double bond, also involved in double bond. So we move towards, we have this possibility and this possibility, and in this case it has 2 hydrogens attached to it, so it cannot make 4 different groups, and in this case it has 2 methyl groups attached to it, so it cannot make it's not chiral, no 4 different groups. So the how many stereoisomers are there? Well, there are 2. There's a cis and there's a trans. So the answer for 26 is B. Okay, 27. How many isometric esters have the molecular formula C4H8O2? Okay, so in this case, the way that I like to solve this question is, let's begin with the longest carbon chain for your acid. So that would be CH3, CH2. Well, how about C over here, and then you have CH3 here. So that's basically a structure that you could, oh my bad, I forgot the 2 oxygens. Okay, so this is one possibility. Right, so in this case, what the acid we have is your propanoic acid, and the alcohol we have is methanol, right? Now, the way that I like to proceed with these questions is, first I make the longest carbon chain for the acid which is possible in the ester, and then I reduce it by 1. So in the next case, I will make it CH3, CO2, CH2, CH3. So in this case, you would have ethanoic acid and you would have your ethanol, right? And if you see, or if you observe, we can also reduce this by one more again. I can make this as HCO2, CH2, CH2, CH3. So all I'm doing is, if you know what, I'm shifting this here, right? I'm shifting the CO2 here. So this is what you get to observe. Now, in this case, this would be your methanoic acid, and this right here would be your propanol. All right. So, yeah, so that's propanol. Now, here's one thing. Before you choose the answer, which is, you might be thinking it's B, wait a second. For now, all I've done is I've shifted the position of the functional group. So this is position isomerism, right? Now, another very important thing to know here is that, this is my technique. Once I'm done with these shifting, what I try to do next is I try to create chain isomerism. So I try to form chains if I possibly can, and if you note, you can actually, and this is how you can. All right, so here's the thing. I have a kind of a very long chain here. If you observe, I have a CH2, CH2, CH3, and if you remember, isomerism starts from your fourth, basically, with 4 carbons. But what I can basically do here is observe this. So how about I have my hydrogen, I keep it here, right? And I have my COO and I keep it here, right? And how about now I take this carbon, which is attached with my functional group, I attach a methane above and I attach a methane below, right? And to complete its valence, I'll add a CH here. Now let's count. I have 1 and then 2 and then 6, and then that makes it 8 hydrogens, 2 oxygens, and then 4 carbons. So that's fulfilled. The molecular formula is fulfilled. And if you observe, the longest chain in this case will be what? 3 carbons. Can't be 4 carbons. So I just made up a chain isomer for this ester. All right, and there's no other possible way that I can make a chain isomer now. And because it said that you should have isometric esters, which means I can't really go into functional group isomerism, because in that case I would be changing the functional group and it would no longer be an ester. So therefore the answer for this would be C. So the technique for esters is, whenever you want to find isomeric esters, make the ester with the longest chain possible for the acid, and then keep on reducing it by one until you end up with hydrogen, which is methanoic acid, and then start off by making chain isomers. Right, so in this case that's the technique that I used to utilize in my time, so I would suggest the same. So the answer is C. Let's move on. It says ethene reacts with aqueous bromine to give two products. These are the products. So you have CH2Br, CH2Br, and CH2Br, CH2OH. This actually happens in the case when you use bromine in aqueous solution, when you put it in water. So because it's your water, it also has it can basically also undergo the electrophilic substitution with your alkene. And this right here happens when you put your bromine in something non-polar, such as CCl4, tetrachloromethane. Now they're saying which statement about these products is correct. Both are formed by, so no, not nucleophilic substitution, because as I said in the very beginning, I showed you that alkenes undergo electrophilic substitution, so that makes B wrong as well. And for C, they say both products can be hydrolyzed to form the same organic compound. Alcohols do not hydrolyze. What hydrolyzes is basically an haloalkane, and when you hydrolyze in haloalkane, its halide is basically replaced by a hydroxide group, or hydroxyl group. Yep. So what you get here is an OH. So all of these bromines will be replaced by OH if we hydrolyze this molecule, because in hydrolysis of your haloalkanes, the halide is replaced by, or the halogen is replaced by the hydroxyl group. So as you can observe, this will give you CH2OH, CH2OH. This will also give you CH2OH, CH2OH. So the answer would be C. For part D, it says both products can form hydrogen bonds with water. Well, this certainly can, because it has a OH group. But in this case, we don't have hydrogen, we don't have oxygen, nitrogen, or fluorine, which is partially negative. So in this case, it cannot be D. And so the answer is C. Moving on. PVC is used as a packing material. What holds the different polymer strands together in a piece of solid PVC? So this is the monomer for PVC, which is your it's basically your chloroethene, and this is what PVC looks like. All right, it has such repeating units. Now it's true that PVC has covalent bonds, but do you really think that different strands of these covalently bonded structures will be held together by covalent bonds? That doesn't actually make sense. It's more like, how do covalent molecules stay intact? Right? What attracts covalent molecules together? And the answer is, if it's covalent, we look for what? We look for your intermolecular forces of interaction, right? And so it can't be covalent bonds, because that's not what holds different polymer strands together. It cannot be hydrogen bonds, because there's no hydrogen attached with oxygen or fluorine or nitrogen. It cannot be ionic bonds, surely, because it's a covalent bonds. And then yes, it can be van der Waal, because that exists in almost every polar and non-polar molecule. So we have to look for intermolecular forces of attraction, because it said different polymer strands, and so the answer would be D. Okay, last question. The diagram shows the structure of buta-1,3-diene. The addition reaction between buta-1,3-diene and two molecules of hydrogen bromide can produce three structurally isomeric products. So we're not looking at stereoisomerism, we're looking at structure isomerism. So it says how many of these products have at least one chiral center. We know that there are going to be three products. That's what they've given to us already, and we just have to see that we have to identify those three different structural isomers, and then we need to decide how many of them have a chiral center. So in this case, I'll start off with the first probability. for the case of hydrogen bromide, what I do is, obviously the addition reaction has to occur across the double bond. So what I do is, I first place the hydrogen on the first carbon and then bromine or bromide on the second carbon, and then I do the similar thing for the other double bond. So I distribute hydrogen and bromide in this way. So hydrogen comes first for both of them and bromine/bromide comes later on. Now in this case, if you observe, this carbon can't be chiral, it has 3 hydrogens attached. This carbon, however, has a methane group attached, a bromide attached or a bromine attached, a hydrogen attached, and also another separate group attached. So this is definitely going to be chiral. Okay, so we know that out of these 3 structurally isomeric products, one of them is definitely, it has a chiral center. And you can see that here I've made the star. So one of the products does have a chiral carbon. Now, the other thing that I can do to, differ this molecule is, when I'm attaching the hydrogen bromide, how about I attach this hydrogen here and this bromine here, but I shift this bromine to this carbon, the third carbon, and this hydrogen to the other carbon. So this is what I am left with, and this one right here is our first product. This right here is the second product. So in this case, if you observe, again, this carbon will be chiral because methane, bromine, and then hydrogen and a separate group. This carbon will also be chiral because hydrogen, bromine, methane, and then a separate group. So now we know that out of these 3, 2 of them do have at least one chiral center. Now we need to look for the third one. And many of you might do this. They might say, okay, well, I shifted this bromine to this side. How about I shift this bromine to this side and this hydrogen to this side now? And if you do that, you will make a very subtle mistake that you might not comprehend. And that is, if you closely observe, you have to be very careful in this scenario. Look here. This is a methyl. I don't know why I keep saying it as methane, but this is methyl. You have a CHBr and then CH2 and then CH2Br. Look here now. You have what? You have CH3, CHBr, CH2, and then CH2Br. Don't you think these 2 molecules are exactly the same? The only difference is you reflected it 180 degrees, right? They are exactly the same molecules. If you name them, they will have exactly the same name. And the thing with isomers is that if they're isomers, they will definitely have different names. But if you name this, you will get the exact same name. And so these are not different. That would be wrong if you went for this possibility. Instead, here's another possibility. And that is, how about I take this bromine, shift it here, and how about I keep this bromine shifted at that side? This is the second one that I made. This is the first one I made. So you can see for this one bromine was on second and the other one was on first. So this was on 2 and then 4. This one was on 2 and 3. So it wouldn't actually make sense to shift this bromine here and then keep this bromine here. It would still be one. It would still be in one way 4, 2. You might say, oh no, well, it's 4, 2, 4, 2, but that's not actually the case. That's not how it works. I hope I'm able to deliver what I'm trying to say here. Well, so this third possibility is definitely different. There's 1 and then there's 4, right? The cool thing that you can do actually is, instead of naming it, just use numbers and put in or plug in your just assign the numbers to carbons and then put in the bromines. All right. So in this case, if you observe now, this carbon has 2 hydrogens, can't be chiral. This carbon has 2 hydrogens, can't be chiral. This has 2 carbons, can't be chiral. This carbon has 2 chirals. 2 hydrogens, can't be chiral. And so this has 0 chiral centers. And so we have only, out of the 3, we have only 2 of them which have chiral centers, and therefore the answer is C. Well, this was a short video for now. I will definitely come up from question number 31 to 40 within the next week, hopefully. And I hope I made these questions clear. If not, my apologies. If you like the video, do give it a thumbs up. Leave a comment down below if you want me to do something specific. And do not forget to subscribe. Thank you. Khuda Hafiz.